Hi everyone. Today we're gonna learn how to find out the working range of working pH range of indicators from the topic acid-base equilibrium. Actually, indicators could be weak acids or weak bases. In this case, we're gonna learn about methyl orange. Methyl orange is actually a weak acid. So if it exists in this form, HIN is red in color, and when it dissociates to give H plus and In minus, which is the conjugate base, In minus is actually yellow in color. So you can imagine in a very acidic medium, because of this, there's a lot of H plus, equilibrium will shift left and it will appear red in color. In an alkaline medium, the OH minus will react with the H plus concentration will fall and the position of equilibrium will shift to the right to produce more H plus, and that's where you see the yellow color, right? So methyl orange actually has a Ka value, but we don't really write Ka, we write it as Kin. So In stands for indicator. So in this case, methyl orange will have a Kin expression, which is H plus concentration times In minus over HIN. So let's look at a typical titration for a strong, maybe a strong acid, strong base titration. Or in this case, let me see. Oh, it's a strong acid, weak base titration. Okay, strong acid, weak base titration. So we can actually use methyl orange as an indicator. So below here, below this line, is more acidic. Methyl orange will appear red. But above this line, if it is more alkaline, methyl orange will appear yellow. So at the end point, where when you're doing this titration, at the end point, it changes from red all the way to orange, and actually that's where you stop. So what is present when you see an orange color? So when it's orange, it means that it must have equal amount of HIN, which is red, and In minus, which is yellow. That gives it the orange color. So if you sub this, since these two values are equal, and you sub back into the Kin, you'll notice that they can cancel out. So what you end up with is actually this expression. Kin equals to H plus concentration at the end point. Right, at the end point, take negative log on both sides, you get pH equals to pKin. So let's go back to the graph. So when it's orange, pH equals to pKin, right? So we actually can find the working range of methyl orange, and this is the formula. pKin plus minus 1. So what we do is pKin plus 1, pKin minus 1. So in fact, this region is actually the effective pH range of methyl orange. Okay, let's see how we can apply this in a typical question. Okay, let's try this question. Most common indicators are weak acids, the unionized molecule being one color while the anion is a different color. Write expression for the equilibrium constant Kin for the above indicator. So this is what it looks like. So from the above indicator, you can see is the product of H plus times I minus over HIN. Alright, so look at part 2. Two indicators of different KIN values are given, bromocresol green and cresol red. Using the values given, determine the working pH range for both indicators where there's a marked color change. So in order to find the working range of the indicator, we're going to use the formula pKin plus minus 1. So let's look at bromocresol green. pKin, since the Ka value is given, alright, Kin value is given, pKin equals to minus log 1.5 times 10 to the power minus 5. And this will give you a value of 4.82. Right? So if you want to find out the working range of bromocresol green, you notice that because you're going to do plus minus 1, so the working range would be 3.82 to 5.82. So this is the working range for bromo cresol green. So let's look at cresol rate. PKIN equals to minus log 1.7 times 10 to the power minus 8. If you work it out, you will get a value of 7.77. So the working range should be 6.77 to 8.77. So for weak acid strong base titration, we know that the equivalence pH would be greater than 7, right? Greater than 7. So looking at the two ranges, the two working ranges, it seems that the most suitable indicator is actually cresol rate because it has it's actually closer to it's at a higher range, right? A higher range because the equivalence pH is actually greater than 7. So pick the one with a higher range. All right. Okay, let's look at part 2 or part 3. Suggest why indicators should be added in small amounts. So indicators are themselves either weak acids or weak bases. So if you add a large amount of indicator, it will definitely affect the final pH and hence lowering the accuracy of the experiment. So they should always be added in small amounts.